Given any three non-collinear points A, B, and C, there exists a unique circle passing through A, B, and C. Now, this is a unique circle, right? If I give you three non-collinear points, there can be one and only one circle that will pass through these 3 points, right? And these 3 points are non-collinear points, all right? So we need to understand two things before proving or understanding this theorem. The first thing is that two distinct lines can intersect at maximum 1 point, right? If I've got any two distinct lines, these can intersect at maximum 1 point. If they intersect at more than 1 point, then these lines have to be coincident lines, right? But these cannot be distinct. I am talking about two distinct lines. They can intersect at maximum 1 point. Another thing that we need to remind ourselves of is that if I've got a line segment, let us say AB, and if I draw a perpendicular bisector, if I draw this perpendicular bisector of this line segment AB, right? This is perpendicular and it bisects AB. So M is the midpoint of AB, right? Then every point on this perpendicular bisector will be equidistant from A and B. Every point on this perpendicular bisector will be equidistant from A and B. Why do I say that? Because let us take any general point P anywhere on this perpendicular bisector. You can take it here, right? Another position of P, and try proving it. You will be able to prove it very easily, right? Because we will look at these two triangles, right? This side is common to both the triangles, and this portion AM is equal to MB, and this angle here is 90 degrees, and this angle is also 90 degrees, because this is a linear pair, and we have already taken this as a perpendicular bisector, right? So if you look at these two triangles are congruent to each other by side angle side congruence criterion, right? Side angle side. Now if these two triangles are congruent, then corresponding parts of these congruent triangles will be equal. So this side AP will definitely be equal to PB. So AP will be equal to PB. That means P is equidistant from A and B, right? This will be true for any other position of P on this perpendicular bisector. Let us take this P1 and join this with A and B. Again, we can say these angles are 90 degrees each, right? This side AM is equal to MB, and this here is common to both these triangles. So again, by SAS congruence criterion, we can say that these two triangles are congruent. Hence P1 is equidistant from A and B, and this will be true for any other point on this perpendicular bisector, right? If we understand these two things, now read this theorem once again. Given any three non-collinear points A, B, and C, there exists a unique circle passing through A, B, and C. So let us take this point as A, this point as B, and let it be point C, right? These are non-collinear. So let us join these points A, B, and C. If I join three non-collinear points, I'll be able to make a triangle, right? So this is a triangle that I've got, triangle ABC, right? Now see, if I draw a perpendicular bisector to this line AB, right? This is a perpendicular bisector. Let me draw a solid line here, right? This is a perpendicular bisector. So I can say any point on this perpendicular bisector will be equidistant from A and B, right? Again, let me take this side now, side BC, and draw a perpendicular bisector to it. If I draw a perpendicular bisector to line BC, now any point on this perpendicular bisector will be equidistant from B and C. Let me join these two perpendicular bisectors. Now let us talk about this point. this point, if I let us say name this point as O, this point O lies on this perpendicular bisector as well as this perpendicular bisector. Now that O lies on the perpendicular bisector of segment AB, so it will be equidistant from A and B. That means OA will be equal to OB. And it also lies on perpendicular bisector of CB, so it will be equidistant from C and B, so it will be OC will be equal to OB. Hence we can say that O is equidistant from A, B and C. That means OA is equal to OB is equal to OC, right? So O is equidistant from the vertices of this triangle A, B and C, right? So these distances are equal. Now if I draw a circle taking OA as radius, OA, OB and OC all are equal. So if I take OA, OB or OC, any of these three distances as its radius and O as my center, I will be able to draw a circle, right? And it will definitely pass through A, B and C. Now why do I say that it is a unique circle? Because when I took a perpendicular bisector of AB and perpendicular bisector of BC, these met at this point O, right? These are two distinct lines and these can meet maximum, these can intersect at maximum one point, right? Because these are two distinct lines. So there is only one circle which is possible through three non-collinear points. I hope you got the idea. What I mean is, let us say you got a triangle, right? If I take a perpendicular bisector of this line and perpendicular bisector of this line, these can meet at maximum one point, right? And this point is equidistant from these three vertices. So there will be a unique circle that will pass through these 3 points, right? All right. Now, another thing that we can learn from this, if I get any circle and I want to locate its center, right? Then how do I do that? I can take any 3 points on this circle, right? Join these points to make a triangle, or I can join these points like this that I've done here and draw the perpendicular bisectors of these lines joining these points, right? If I draw these perpendicular bisectors, these will definitely meet at the center. So if you are given any circle, right, or if you draw a circle using your bangle, let us say, and you want to find its center, you just have to take 3 points, right, join these to make any two line segments and take their perpendicular bisectors. The meeting point of these perpendicular bisectors will be the center of this circle. One more thing that you can understand using this theorem is that if you got an arc, let us say you got this arc, right? This arc will belong to a unique circle, right? There cannot be two different circles having this arc, right? There can be one and only one circle, because on this arc you can locate infinite number of points, and if you take any 3 points on this arc, you will be able to draw two line segments like this, right? And if you draw their perpendicular bisectors, these will be two unique, two distinct lines, and they can meet at maximum one point. So this will be the center of the circle of which this is an arc. So you can complete the circle using this as your center and this as your radius. So this arc, that means two different circles cannot have a common arc, right? So what can we write? Let us write these points as corollaries to the theorem that we just proved. If two circles have 3 points in common, 3 points in common, then they must coincide. That means there cannot be two different circles having 3 points in common. If there are 3 points in common, then we can say that these must coincide, right? These two circles are nothing but coincidental. These lie on each other completely. Okay. Or in other words, you can say two different circles may intersect at maximum 2 points. At maximum 2 points, right? And another thing that we learned was two different circles cannot have a common arc. We are saying the same thing in different words, because if two circles have a common arc, then that means they have more than 3 points in common, so they must coincide, right? All right, so this was about this theorem.